Hello all. Today I will go over the second part of our chapter 2 review from our textbook. If review A went through the theoretical part, most of them, then in this review B we will go over mostly word problems. Okay, let's see number 72. A particle moves along a horizontal line such that its coordinate at time t is given by that. Okay, let's see. So suppose this is the horizontal line, right? And at time 0, when t equals to 0, x is equals to b, huh? The position b at time 0. t0, I think I should say x0. x0 equals to b at time 0, right? Okay, now then find the velocity and acceleration function. So part A, the velocity is equal to the derivative of that position function, where x is, let me rewrite it using rational exponent. So the derivative of that will be 1/2 b squared plus c squared t squared to the power of negative 1/2 times the derivative of b squared plus c squared t squared. This is equal to derivative of this. This b squared is constant, so the derivative is 0. And then there will be 2c squared t, 2c squared t over 2 square root of b squared plus c squared t squared. I can cancel the 2's, so I get c squared t over square root of b squared plus c squared t squared. That's the velocity functions. Yeah, we can just stop there. But for the purpose of our next step, finding the acceleration function, I need to do further derivative from there. So the acceleration function will be, I need to do the cross product rule, this guy times this guy. So the first one will be c squared t prime times b squared plus c squared t squared to the power of 1/2 plus c squared t times the derivative of that b squared plus c squared t squared to the power of 1/2, which is the position function, Okay, so this will be c squared times square root of b squared plus c squared t squared plus c squared t times the derivative of position, which we have had earlier, is c squared t over square root of b squared plus c squared t squared. Let's do LCD. So if I do the LCD, the denominator is b squared plus c squared t squared. On the top, I multiply by square root of blah here. So it becomes c squared b squared plus c squared t squared plus c to the 4th t squared, which simplifies to be b squared c squared plus, we get one of the c to the 4th t squared here and another one there, so 2c to the 4th t squared, oh no, yeah, t squared over square root of b squared plus c squared t squared. Okay, that's the acceleration function. And part B, show that the particle always move in the positive direction. basically moves in the positive direction means the velocity is always positive, huh? Right? That's what we need to show. Okay, so we see the velocity is c squared t over square root of b squared plus c squared t squared. Okay, note that, and the t is non-negative, right? Okay, so notice that b squared plus c squared t squared is always at least b squared, which is positive, right? And since t is at least 0, then c squared t is also at least 0. So consequently, therefore, phi t is non-negative for t at least 0. That's for number 72. Number 73, I usually don't do odd numbers, right? But let's try to apply this even further. Now, a particle moves on the vertical line. Oh, this time it's vertical line. So that its coordinate at time t, so y as a function of t is t cubed minus 12t plus 3 for t non-negative. So actually from there we see the y at 0, when the time is 0, the position is 3, huh? Okay, so find the velocity and acceleration function. It's polynomial, so it should not be too hard. Like the velocity, the y prime will be 3t squared minus 12, while the y double prime, the acceleration, this is the phi t, is 6t. Now, when is the particle moving upward and when is it moving downward? So part B, upward when the y prime t is positive, right? So 3t squared minus 12 is positive. Let me factor it. Okay, so from there we see that the critical points is when t equals to -2 and t equals to 2. But t equals to -2 doesn't count though. Oh, well, anyway, let me just go on with the sine graph. When t equals to -2 and t equals to 2, the velocity are zeros. This is positive, negative, positive. But our domain is actually just from 0, huh? Okay, so it is moving upward when the inequality is positive. So upward on it's greater than 0, huh? Okay, on the interval 2 to infinity, and downward on 0 to 2. That's when it is negative. Okay, that's for part B. Part C. Let me do it here. Part C. Find the distance that the particle travels at the time from 0 to t equals to 3. Well, we know that between 0 and 2, on interval 0 to 2, it's moving backward. So at time 0, it's at 3. Okay, let's see what happened at time 2. So y2 equals to 2 cubed minus 12 times 2 plus 3, that's 8, minus 24 plus 3, It's 11, so negative 13. So at time 0, it's here, and then at time 2, it actually goes to negative 13, huh? So it travels 16 units, right? Okay, and then later on, at time 3, we need to then see when y equals to 3, it will move forward, but where is the location? So that's 27 minus 36 plus 3, that's negative 6. So at time, this is at time 2. At time 3, it will be at negative 6. So it moves here. That's at time 3. Okay, so and then from 2 to 3 forward. Okay, so it travels how far? Between 3 to negative 13, and then from negative 13 to negative 6. That's how far it travels. So that's 16 plus 7. That's 23 unit. Okay, now, and part D, graph the position, velocity, acceleration function for that. In our textbook, this actually has a graphing notation. Okay, so I would just do the graphing. I think it's not too hard to do it by hand, just for the derivative and second derivative. So let's say this is our t-axis, and this is the y prime, y double prime axis. Then at let me graph this first derivative. The first derivative, 3t squared minus 12. So approximately 3t squared minus 12. The y-intercept is 2. So the first one is approximately. I'm sorry, I cannot really. I try to get something nicer. I guess not, huh? So let me just do it this way then. So it's approximately like this. Okay, this is the y prime, which is the velocity. Okay, this is at negative 12. And then the y double prime is 6t. So let me use this slightly different color. Maybe this one here, the 6t. That's a 6, that's 12. So that's a vertical line. I mean, that's just a line. Looks like this. This is the y double prime t, which is the acceleration. Okay, and then the y cubed minus 12t plus 3. So it will follow the cube according to what we have before. It starts at 3, and at 2 it reaches negative 16, huh? So it looks like this. And then at t equals to 3 it reaches negative 6. Yeah, okay, it maybe look like this. Yeah, according to what we have from what we have here, right? From what we have here, we see that yeah, it has horizontal tangent line at negative 2 and at 2, right? Horizontal tangent line at 2 and negative 2. Let me move this part down. Okay, but we start with t equals to 0, right? So this is the y t. Okay, and this is when t equals to 2. When t equals to 2, the y equals to negative 16. And when t equals to 3, the y equals to negative 6. Okay, so the yt is the position, y prime t is the velocity, and y double prime t is the acceleration. That's for number 73. Oh, you know what? I have, that's part D, huh? This is part D. When is a particle speeding up? When is it slowing down? Well, speeding up means the speed is increasing. Speeding up. Which means the speed, the velocity is increasing. Okay, if the velocity is increasing means the acceleration is positive. Okay, as you can see, the acceleration is always positive, right? The acceleration is positive. That's increasing. That's for t greater than 0. Okay, and never slowing down. Is it okay? There could be another interpretation for this though, but the way I see is to say that it is speeding up means the velocity is increasing, right? But that's my interpretation of this question. But there's another way to look at that speeding up, because they use the word speed. Okay, we may see that as speeding up as the second interpretation. The speeding up means the speed is increasing. The absolute value of Vt is increasing. Okay, now if we take a look at the absolute value of Vt, then we cannot avoid to do the absolute value of that Vt, which is like this, right? Basically, I reflect this part here with respect to the x-axis. Okay, now, and the Vt is increasing when the magnitude is positive. No, I should not say the magnitude of positive. The derivative of that is positive. Okay, the derivative d absolute of Vt dt is positive. The slope of that derivative is the slope of this graph here. The slope of this graph here is positive. And if that's the case, then we see it only happens at from t equals to 2. Okay, from t equals to 2. That's the slope of absolute of Vt to be positive. That's only happen when t start from 2. Okay, that's my interpretation though. Okay, I tend to go with the first interpretation, but if we look at this word speeding up coming from the absolute value of the velocity, then yes, that's we need to follow the second interpretation. Okay, and then that also implies, so slowing down is from 0 to 2. Okay, yeah, that's for this question here. Number 74. Volume of a right circular cone is given by that function pi r squared h, the volume. Okay, with the radius r for the base and h for the height. Now find the rate of change for the volume respect to the height if the radius is constant. So part A, we need to find d phi dh. if the radius is constant. So we do the derivative of this respect to a constant. Oh, but this is the variable h only, huh? Only h. So it becomes just the coefficient only, huh? While part B, find the rate of change of the volume respect to the radius if the height is constant. Derivative or the rate of change respect to the radius. So we see this as 1/3 pi h r squared. When we do the derivative, we copy the coefficient first times the derivative of r squared, which is 2r. That's 2/3 pi r h. Oh, that's it for number 74. Easy. We don't need to apply any numbers. Number 76. The cost in dollars of producing X units of a certain commodity is, let me copy down the cost function. That's 920 plus 2x minus 0.02x squared plus 0. How many zeros after decimal point? 4, huh? 1, 2, 3, 4, 7x cubed. Part A, what is the marginal cost function? That's the first derivative respect to x. That's 2 minus 0.04x plus 0.00021x squared. Find C prime 100 and explain its meaning. C prime 100, when I replace x by 100, this is 2 minus 4 plus 1, 2, 3, 4 plus 2.1. This is 0.1. I think so. Yeah. Okay. Explain its meaning. This is the marginal cost when we are producing 100 units, right? So what is marginal cost? It says the cost, the increase or decrease if negative, the increase of cost for producing an additional item when producing 100 items. Like let's say right now we already produce 100 items and then somebody asks, can you make one more for me? You know, then of course producing that one more item requires extra cost, right? Okay, now that extra cost is not only the cost for the producing that one item, but additional cost of the cost that we already have. Yeah, how to say that? So let's say there's a cost for producing 100 items. To produce 100 items. Okay, of course, producing 101 items has different costs, right? Okay, now then to produce that, the next one items will cost us additional how much money? Okay, so that's from the limits, from the derivative point of view. Now part C here, compare the C prime 100 with the cost of producing 100 first item. So to produce cost, the actual cost, this is where you will see that the derivative is basically just estimate, right? Cost of producing 100 first item is the same to the cost of the total cost to produce 101 item minus the total cost to produce 100 items. The difference between this. Okay, if you copy this in here, this will be the extra cost. This is the extra cost to produce that additional item. Okay, and that is basically by plugging numbers. So this is let me do it this way. So this is 920 plus 2 times 101 minus 0.02101 squared plus 0.00007 101 cube minus 920 plus 2 times 100. This is the cost of producing 100 items. Okay, now you see, at least theoretically, before I start using my calculator, notice that these two cancels here, right? Okay, and these two here will give us, you know what, let me just keep using red. This guy here will give us 2 minus 0.02 times the difference of this. 101 minus 100, that's 201. And then plus 0.00007 times 101 cube minus 100 cube. So at least now I localize what I need to compute, huh? So that will be 4.02 plus 0.00007 times, now time to use calculator. Where's my calculator? So 101 cube minus 100 cube. 30301. This is 30301. And then I want to multiply that by 0.00007. That's 2.12107. Am I copying it correctly? So putting things together, that will be 2 minus 4.02 plus the last answer is 0.10107. That's 0.10107. That's the actual difference. That's the actual extra cost of producing that one extra item. Okay, which is fairly well estimated by using the first derivative, which gives us the marginal cost. Okay. Number 77. The volume of a cube is increasing at the rate of 10 centimeter cube per minute. Oh, okay. So the volume of a cube with side S, let me use A instead of A. So let's say we have a cube. Try to visualize that, right? Let's say we have a cube with sides with HA. Okay, we know that the volume is A cube, right? Now, according to this passage here, it says that the volume respect to time, the change of the volume respect to time is increasing at 10 centimeter cube per minute. Okay, the question is, how fast is the surface area increasing when the length of the H is 30? So at A equals to 30, how fast is the surface area increasing? Oh, that's a hard question, huh? That's a hard question. How do we do this? Honestly, I don't see the relationship between dv and dt though. But you know what? Let's do it this way. Uh, if the volume is a cube, then the derivative of the volume respect to time will be 3a squared times the change of a respect to t. Is it right? Oh, I think that's where we get it then. Because this is equals to 10 and dA equals to 30. Then we find the change of the h, how fast the h is changing. Is it right? That's 10, and this is 900 times 3, 2,700 dA dt. So dA dt, I'm sorry, let me scroll up a little bit. dA dt will be 10 over 2,700, or simply 1 over 270. This should be centimeter per minute. That's the unit. Okay, now how about the surface area? Surface area of a cube will be, there are 6 surfaces, all of them with area a squared. So ds dt, the derivative, the change of the surface area respect to time will be the derivative of this respect to time. That will be 12a times dA dt by chain rule. Okay, oh, now we get it. That 12 times 30, that's the A, and the ADT, we got it earlier, that's 1 over 270. Okay, with 30, that's, let me just multiply this. This is 360 over 270. The units must be centimeter square per minute. All of them multiple of 90, reduced by 9, that will be 4 over 3 centimeter squared per minute. Okay, I hope I don't make any miscomputation. I think I should be okay. That's for number 77. Number 78, a paper cup has the shape of cone with height 10 centimeters. Okay, let me draw that cone first. A paper cup with cone, the height is 10 centimeters. The radius at the top is 3 centimeters. Okay, now if the water is poured into the cup at the rate of if the water is poured into the cup at that rate, that will be dV dt, huh? The change of the volume, and it is increasing. That will be 2 centimeter cube per second. How fast is the water level rising when the water is 5 centimeter deep? So when h equals when the height of the water is equals to 5 centimeter. So let's say we have some water here, right? There's some water level there, and this is 5. Okay, Of course, the shape of that water there will be in the shape of the cone also. Is it right? But at that height, the radius will not be 3 centimeters. Let's do some similar triangle approach. So I wonder if I can get the shape. Okay, well, this is the water. If this is height equals to 5, what is the radius? Compared to the shape of the cone, if the height equals to 10, the radius is 3. Okay, so by using similar triangles, we get r, the radius of the cup, I'm sorry, the radius of the water, not the cup. the radius of the water over the height of the water should be equal to the radius of the cup over the height of the cup. Okay, so that's RW over 5 equals to 3 over 10. I think you can just conclude right away that it reduced by 2, right? So the radius of the water at that time is 1.5 centimeter. Okay, what we are interested in is the change of how fast the water level rise. So we want to find dH dt equals to what? Is it right? So at that time, how fast the water level increases. So the volume, as we know, is 1/3 pi r squared times the height. Is it right? So we want to find how fast the water level rising. So we want to find dH dt. But if I do the derivative with respect to the volume, I mean with the derivative of the volume with respect of time, I need to do product rule. dV dt equals to product rule 2 over 3 pi r h dr dt plus 1/3 pi r squared dH dt. Okay, we know this is 2. How fast the radius increasing though? Do we know that? They don't tell us, huh? Let me plug in number first. So this is 2 power of pi. The r is 1.5. The height is 5. So 1/3 pi 1.5 squared dH dt. I think we cannot really do this yet until we say that I need to find the RDT though. Yeah. So if we suppose if just I think for this question here, if dr dt equals to 0 means the radius is assumed not to increases, then the equation becomes 2 times 1/3 pi 1.5 squared dH dt, and solving this for dH dt will give us the answer. So this will be 6 over pi times 1.5 squared. That's our dH dt. Okay, let me use calculator to compute that. 6 divided by parentheses pi times 1.5 squared. So 0.84883. 0.84883 centimeter per minute. That's the dH dt. If we hold, assuming the radius is constant, which is not true because of course as the water level increases, not only the height increases, the radius also increases, right? Okay, unfortunately at this point I don't have a way for me to compute this dr dt. They're supposed to tell us though, yeah, which they don't, right? Which they don't. Oh, you know what? I just realized. Actually, they did tell us the radius. When the water is 5 centimeter deep, we can actually find the volume. Hold on. I need to. Here's the thing. So when the height of the water is 5, we can actually find the radius and find the volume. Therefore, we can express this volume fully as a function of height without the radius. You know what? Let me redo this. This is simply because I have the r there is not right. Or you know what? Let me keep it that way. Let me keep it this way for now. Hold on. So, but the mistake is here. I cannot assume this equals to 0. So let me erase from here. What I know is from here the radius of the water over the height of the water equals to 3 over 10. In other words, the radius of the water equals to 3/10 of the height of the water, right? Okay, so what happened then, if I do the derivative of the radius of the water respect to time, that will be 3/10 times the derivative of the height of the water respect to time. This is 3 over 10 dH dt. That's what I will use. So this will be 2 equals to 2 over 3 pi times 1.5 times 5 times 3 over 10 dH dt plus 1 over 3 pi 1.5 squared dH dt. Okay. Yeah, I know it's complicated, but notice that 2 over 3, 2 times 1.5 is 3, cancel with that 3, right? So I get what, and then this cancel with this is 2, so I get 3 pi over 2 dH dt plus 1.5 is basically 3 halves, so 1 over 3 times 3 half being squared, so that's 3/4 pi, 3 pi over 4 dH dt. This is equals to 6, that's 9 pi over 4 dH dt. So dH dt, the change of the height respect to time will be 8 over 9 pi. Okay, which I think will be a lot easier if we have converted this, all of this, we change the radius here in terms of height. So this is 1/3 pi 3 over 10 height squared times the height. So what will that be? That will be 3 pi over 100 h cubed. Yeah, if we use that, I think it will be easier. So d phi dt will be 3 pi over 100 times 3h squared dh dt. Okay, so that will be 3 pi over 100 times 3. The height is 5, so this is 5 squared. H dt, while we know the change of the volume is 2, as I remember earlier. Yeah, it's 2. Okay, so it's 25, 9, 4. So this is 9 pi over 4 dH dt equals to 2. So dH dt equals to this. I think that way is easier. Yeah, that way is easier. You know, yes, I was reluctant to say that the change of the radius respect to time is 0. That's not appropriate. We know it will change as the water increases. the radius supposed to also increase. That's for number 78. Number 79, a balloon is rising at a constant rate, 15 feet per second. So let's draw a balloon. So this is the balloon. Okay, it is increasing at 5 feet per second. A boy is cycling along a straight road at the speed of 15 feet. So let's say we have a boy going to that direction at 15 feet per second. When he passes under the balloon, so right it is when it is below the balloon, the distance is 45 feet. How fast is the distance between the boy and the balloon increasing 3 seconds later? 3 seconds later, then the height of the balloon will be 45. The height will be 45 feet plus 5 seconds times 3, right? Because it is increasing, the balloon is increasing at 5 feet per second, right? 3 seconds later, then it is, the position is already times 3. So that will be 60 feet. The height is 60 feet at that time. Okay, and the boy is no longer right below that. It's already somewhere to the, let's say to the right here. Okay, that will be, the distance here will be 15 times 3, which is 45 feet. Now what they want is how fast is the distance between the balloon and the boy increasing 3 seconds later. Okay, let's call this D. So the D squared equals to the height squared plus the horizontal distance squared. What do I want to call that? You know what? Let's call that X. Okay. What we are interested in the distance. Oh, you know what? Let's call that Z then instead of D. So because we use D for the differential, right? Let's call that Z. So the change of the distance Z respect to time is the one in question. Okay, let's do implicit differentiation from there. So 2c dc dt equals to 2h dh dt plus 2x dx dt. We can cancel the 2's, right? Okay, so this is becomes z times dc dt plus equals to h times dh dt plus x times dx dt. When I plug in numbers, the one in, I don't know the z, but if this is 45 and this is 60, this is 3 times 15, 4 times 15, then the z must be 5 times 15, This is 5 times 15 dz dt equals to the height, which is 4 times 15 dh dt plus dx is 15 times 3 dx dt. So again, we can cancel the 15, right? And actually, I can also plug in dh dt. The height increasing at 3 feet per second, and dx is increasing 15 feet per second. Okay, let me mark that I cancel the 15. Divide by 15 each term, right? Okay, and then when I plug in numbers, dc dt equals to 1 over 5 times 12 plus 45. Is it right? Okay, 57 over 5. That's 11.4 feet per second. Okay, that's for this. So we create the right triangle first, right? Okay, that gives us this Pythagorean situation there. Okay, so you see that the length of this x is increasing at 15 feet per second, and the length of the height for the balloon is also increasing at 5 feet per second. Hold on, I think I used wrong number here. It should be 5 here. It should be 5 here. So this will be 20. That's 65 plus 5. 65 divided by 5. That's 13. So that's 13. Yeah, good thing I checked my. I look at that question again. Yeah. Okay. And for that reason, the length of the distance will also increases, right? That's the one in question, how fast it is increasing. Okay. Now that's for number 79. Number 80. A water skier skies over the ramp shown in the figure at the speed of 30 feet per second. How fast is she rising as she leaves the ramp? Oh wow. So at this point here. So this is 15 feet. This is 4 feet. Okay, let's call this the x, and let's call this the y, and this is z, right? Okay, notice that they tell us that dc dt equals to 30 feet per second. We want to know how fast it is increasing. Dy dt equals to what as she leaves the ramp. Okay, use Pythagorean theorem again. So c squared equals to x squared plus y squared. So 2z dc dt, the derivative with respect to time, dx dt here, plus 2y dy dt. I honestly don't know how to do this one though. Huh. Really, I really don't know how to do this one. I know this guy. I know this guy. I can compute the c. I can compute the x. I can compute the y. I mean, I know the x. I know the y. But I don't know the dx dt. So I cannot find the dy dt then. How to do this one? Let me think a little bit. Unless I have a wrong assumption. Hold on. I think I make a wrong assumption. So, when we say 30 feet per second, is it this horizontal speed, which is dx dt? Or is it the speed over the ramp, which is dc dt? That's the one I think I'm confused. Because here's the thing. Why I say if I use this assumption, right? This is the speed, right? The slanted speed, the 30 feet per second. then how fast it is increasing is basically dy dt will be 30 feet per second times 4 over 15. Oh, no, not 4 over 15, 4 over the square root of that, square root of the Pythagorean. 4 over square root of 15 squared plus 4 squared, which is basically the cosine or the sine of the angle, theta here. Okay, that's what I think it will happen. Yeah, basically that the slanted speed 30 feet per second is being decomposed into the horizontal speed and in the vertical speed, right? Okay, is that the question though? So I have issue with this. That's my question. Is this the statement, or is the 30 feet is actually the one going into the ramp? Okay, the one going into the ramp. Let me think about that. I will pause the recording a bit. I think that's really the case. I have no way to find if this is the dx dt, then how do I interpret dc dt? I don't think that's the way to do it though. So I have to go on with my original interpretation. Okay, I will go on with my original interpretation, which basically says that dc dt is 30 feet per second. We want to find dy dt. That's what I think I will do. Okay, that's my scratch, but let's do it properly. Notice that the y over z is equals to 4 over the square root of 15 squared plus 4 squared, right? So y equals to 4 over, what's that, 225 plus 16, 241, square root of 241 equals to z. Okay, notice that this 4 over square root of 241 is the same to that, which is the sine value of the sine value of the angle. We don't need to worry about the angle actually though. So dy dt equals to 4 over square root of 241 dc dt. Now, if the speed over the ramp is 30, so I multiply this by 30. Then I will get 120 times, 120 over the square root of 241 feet per second. That's the speed, increasing speed. The speed of going up, that how fast it will go airborne, right? Okay, that's for number 80. Again, this is with the assumption that the 30 feet is the one on the ramp. Okay. Number 82. Find the linear approximation of this function near x equals to 3. So fx equals to square root of 25 minus x squared. We will linear approximation basically find we can think of that as a equation of tangent line. At x equals to 3. Okay, so f prime x equals to, this is 25 minus x squared to the power of 1/2 This is 1/2 25 minus x squared to the power of negative 1/2 times the derivative of inside, that's negative 2x. So that's negative, the 1/2 cancels, x over square root of 25 minus x squared. Okay, near 3, so f prime 3 is negative 3 over square root of 25 minus 9, that's 16, negative 3/4. Okay, so y, you know what, I need to first find what is f3 though. f3 equals to 4, huh? f3 equals to 4. Since f3 equals to 4, then the equation of the tangent line is given by y minus 4 equals to negative 3/4 x minus 3. Negative 3/4 x plus 9 over 4 plus 16 over 4 is 25 over 4. In other words, now we can linear approximate that. The linear approximation of that function near 3 will be negative 3/4 x plus 25 over 4. Okay, or you may consider leaving it this way. Linear approximation of that curve near 3 will be negative 3/4 of x minus 3 plus 4. Actually, yeah, yeah. You can just leave it like that. Okay, because we want that to be near 4, near x equals to 3, right? Okay, illustrate part A by graphing f and linear approximation. The linear approximation. I need to. Well, okay, so square root of 25 minus x squared is the positive y component of a circle with radius 5 center at origin. That's what it looks like, right? Okay, now at this point x equals to 3, you have a tangent line. This is the linear approximation approximated using our tangent line. Okay, now part C, for what values of x is the linear approximation accurate to 0.1? Okay, so if we want the accuracy of 0.1, then what is the interval such that the error we have between the tangent line and the curve is less than 0.1? In other words, the error should be absolute of the error should be less than 0.1, the y value, okay, which is absolute of square root of 25 minus x squared minus the approximation using that line is less than 0.1. Okay, we need to solve for x there, which I don't think I will do. But that's basically what it means. What you can do, however, is use graph. You know what? I do it. Let me grab my graphing software. I hope that's what we see here. Is it the one we see together? Okay, so I am going to graph y equals to the square root of hold on, special keypad. The square root of 25 minus x squared. Okay, and the other graph is the linear approximation. Okay, negative 3/4 of x plus 25 over 4. Okay, that's what we have, right? Okay, now what I'm gonna do is I move this semicircle up and down by 0.1. Okay, and then see where where's the maximum minimum value for that. So I will copy this. Give me a second. I will copy this guy here and make it new expression plus 0.1 and then subtract by 0.1 as well. The new expression again. Subtract by 0.1 and then I supersum that part. Oops, too much. To see where they intersect. Okay, so the purple one is the original function, right? The blue one is the above. It intersect at approximately 3.7, less than 3.7. Okay, and at 2 point, what is this? I can't really see it better, huh? 2.25. 2.25 and 3.65. 2.25, 3.6. You know what? I wonder if I can make it a bit smaller and then screenshot this part and then put it back to our notes. Yeah, so what I meant is this. So this is the linear approximation here. Okay, it intersects with the band that we tolerate 0.1. This is the band or the tape, if you like to call that, right? Above the okay, this is the tolerance levels less than 0.1. Now, according to what we see here, the intersection of the tangent line to the edge there is, yeah, so this is this is when x is approximately 2.2, huh? 2.2 something, 2.25, and this one here is approximately x is approximately 3.6. Let's call it 3.6 and 2.3. Yeah, so from the graph uh, the error will be less than 0.1 if we try to estimate that using x between 2.3 and 3.6. Okay, now you notice that this question here, this in part C, this question here, part C here, is a question that I cannot ask you during the test because I don't allow you to use graphing calculator, right? Okay, yeah, but basically it is done by solving this inequality here. It is done by solving that inequality. Okay, which then a lot of approximation. Okay, number 83. Find the linearization of that at x equals to 0. State the corresponding linear approximation and use it to estimate the value of 1.03. Okay, let's try. So fx equals to the cube root of 1 plus 3x, which is 1 plus 3x to the power of 1/3. So f prime x is 1/3 1 plus 3x to the power of negative 2/3 times the derivative of the blah, which is 3. That cancels, huh? Which is 1 over square root of, cube root of 1 plus 3x being squared. Okay, because the 3 cancels, right? Now then, so how about the tangent line? Equation of the tangent line, which give us later on the linear approximation is, oh, I need to first compute what is f0. f0 is 1. So f0 equals to 1. Okay, so consequently, y minus 1 equals to, what is f1? It's also 1, huh? It's 1 times x minus 0. So basically, y equals to x plus 1. Oh, I don't expect that though. At 0. Am I doing it right? Seems to be, but I think I'm correct. Okay, now, so the linear approximation is given by x plus 1. Okay, next, use that to approximate 1.03. So the linear approximation at 1.03 will be 1.03 plus 1, which is 2.03. Okay, let's ask ourselves what is the actual value. The value of 1.03 for that function, that's cube root of 1 plus 3 times 1.03. That is the cube root of 4.09. So 4.09 to the power of 1 over 3. 1.59922. Huh? 1.59922. That's a very off estimate. Did I make anything wrong? Oh. So I'm sorry. So no, I don't replace this by 0.1.03. What am I doing? So that's my x when x equals to that. So my x here will be no. So I'm sorry, I make a mistake. The square root of cube root of 1.03 corresponds to the x equals to 0.03, 0.01. Yeah, because this is 3 times 0.01, right? What am I doing? Okay, so yeah, this is the, so linear, this is also incorrect. This part here is supposed to be 0.01. That's 1.01. I was wrong with the x input. What am I doing? Yeah. Again, 1.03 corresponds to x equals to 0.01. Okay. According to our calculator, so 1.03 taken to the power, what am I doing? 1.03 taken to the power of 1 over 3. That's 1.00990. 1.00990. Oh, not too far, huh? That's a 0.00007 off. Okay, now for part B, that's basically we need to use graphing software. We basically want the error to be within 0.1, which means the difference between the actual value, the cube root of 1 plus 3x, and the approximation x plus 1 is less than 0.1. Okay, so at which interval is this true? Okay, similar to the one I did up here, we basically do the graphing and see in which interval the graph is within the band. Maybe here. Oh, I should not. Oh yeah, I can. Yeah, so it is within the band in this interval here. Okay, yeah, so you basically do the graphing then. Number 84, I think that's the second from the last question. Number 84, find dy if we have this function. I do it the derivative. The dy dx equals to 3x squared minus 4x. Okay, which means dy, the differential of y equals to 3x squared minus 4x times the differential of x. Now from here we plug in numbers. Just that simple. Okay, and x equals to 2, dx equals to 0.2. Okay, so 3 times 2 squared minus 4 times 2, all of them multiplied by 0.2. So basically, if we have this function, y equals to this guy, then how much the y changes when the x is equals to 2 and the x is increasing by 0.2. The dx is positive 0.2. Okay, so 12 minus 8 is 4 times 0.2, that is 0.8. Okay, the last question, let me move this here to save some space. Suppose f is differentiable function and f g x equals to x. Show that g prime equals to that. Let's do implicit differentiation. Implicit differentiation with respect to x. Then the right hand side derivative of 1 respect to x, derivative of x respect to x is 1. The left hand side we need to do chain rule, huh? So this is f prime g x times g prime x. Is it right? Okay. Now then g prime gx, we know g prime x equals to 1 plus fx squared. So right. So this will be 1 plus f of g of x squared times g prime of x. Okay, see, fx, the prime of that is 1 plus the function being squared, right? So if I change this to g here, this becomes g here. Is it right? Okay, but at the same time, we know f compose g is equals to x. So this guy becomes 1 plus x squared times g prime of x equals to 1. So g prime of x equals to 1 over 1 plus x squared. Oh no, I don't have square. The square is here, by the way, not outside. Yeah, so not here. Okay, and that's it. That's the end of our chapter 2 review, the second part. So long.